This Chapter 1 reviews the relationship between credit pricing and the key credit fundamentals of default probability and recovery value using what is known as a risk-neutral framework. We begin by examining the simplest possible credit instrument under the simplest possible market conditions. This is a $1 one-year instrument that pays no coupons prior to its maturity and contains no covenants or other clauses that might allow the holder to declare a default prior to the maturity date. So at maturity, the instrument pays either $1 plus the coupon, or it defaults and trades at a price of 40%, say, of the total claims under the instrument, including accrued and unpaid interest. No other scenarios are possible. The probability that the instrument will default at maturity is assumed to be 6%. The instrument is to be issued at par, and you are asked to calculate the minimum coupon that would be acceptable to you to purchase the instrument, knowing that the one-year risk-free rate at that time is 5%. The tree you see here describes the two possible states for this instrument: default or full payment, with probabilities of 6% for default at the bottom and 94% for full payment at the top. This enables us to calculate the expected value at maturity of the instrument by multiplying the probability of each scenario by its outcome. We now simply discount this amount at the risk-free rate of 5%, appearing on the right of this equation, and set it equal to the issue price of $1, obtaining the formula you see here, which leads to C, the coupon, being 8.92%. Generalizing the case using PD for the one-year default probability, FV for the face value in dollars, RV for the recovery value in default, expressed as a percentage of each dollar of outstanding claims, whether for principal or for interest, PV for the issue price per $1, and RFR for the one-year risk-free rate, allows us to write this equation here, which again you can confirm is obtained simply by setting the probability adjusted payoff at maturity, discounted at the risk-free rate, to equal the PV. Note that we have used here a term PS for the survival probability, and that is nothing more than 1 minus PD for that same one-year time interval. Rearranging some of these terms enables us to derive a general formula for the coupon, reflecting all of the terms PV, RFR, PS, FV, PD, and RV. And this formula has been programmed in Excel in worksheet coupon. On this worksheet, coupon, you should please be careful when using it to ensure that you input the data in the correct units. The worksheet allows you to stipulate any face value for the bond that you desire as a dollar amount. So we'll go ahead and put $1 here, while the issue price, recovery value, and risk-free rate must be inserted as percentages. So our issue price here is 100%. Our recovery value, of course, is 40%. And our risk-free rate is 5%. Of course, the default probability is also expressed as a percentage, and we know that this number was given as 6%. The worksheet then calculates the coupon as a percentage of par, appearing here in cell C12 as the 8.92% that we had calculated previously. When we call this type of analysis a risk-neutral analysis, we mean that it treats the coupon as compensation only for the instrument's expected credit losses and not for any other factors such as the uncertainty of returns, liquidity disadvantages, regulatory or accounting issues, etc., which will be analyzed in Chapter 2, where we seek to determine how much of a role they play in the pricing of credit instruments. It should not take you long to realize that we can apply the reverse of this analysis to calculate the implied default probability if we know the recovery value and the coupon. The credit industry has felt more comfortable assuming a standard recovery value in default, usually of 40%, but with some exceptions, and then implying from the coupon a default probability. So we will illustrate this process next with a short quiz question. Here is the quiz question. Subject to the same assumptions as before, calculate the implied PD of a one-year bond issued at 98 and paying $100 of principal and $8 of coupon at maturity. Assume recovery value in default is 40% of par and that the risk-free rate is 3%. On worksheet coupon, we solve for the PD after inserting 98% for the issue price in cell C9, 40% for RV, which we have already, and 3% for risk-free rate. And right now, we are getting a coupon of 4.71%, which is not the stated coupon. So we resort to goal seek and set this cell C12 equal exactly to 8% by changing the cell for the default probability, which is cell C4, yielding for the PD a value of 10.91%. Those of you who have familiarity with the goal-seek function will understand that occasionally, depending on the level of accuracy at which goal-seek has been set, the solution found in this example here may differ ever so slightly from the data provided at the beginning of the problem. We now apply essentially the same logic to derive the appropriate spread for a CDS if we know the PD and RV of the reference entity. So again, assuming PD is 6% and RV is 40%, we draw this diagram which shows the possible outcomes for the two parties under all possible scenarios, again subject to the same assumptions as before. Here S on the right is the spread paid by the protection buyer under the CDS, expressed as a percentage of the contract's notional amount. Note very importantly two things specifically that this diagram assumes. First, that the spread is paid only annually, which in this case means at maturity of the contract, and not semi-annually or quarterly or monthly, which of course it could be. And two, more importantly, that if a credit event has occurred by the maturity date, the buyer nonetheless pays to the seller the spread that has accrued up to the date of this credit event, at the same time as he is receiving from the seller the negotiated compensation for the credit event. This second assumption is consistent with market practice in some jurisdictions, but not in others, where the spread from the protection buyer that has accrued since the last payment date is not paid once a credit event occurs. The different alternatives for settling a CDS following a credit event are discussed more extensively in our earlier module labeled Introduction to Credit Default Swaps. Now, using the normal assumption that any financial bilateral contract that is properly priced must satisfy the property at inception that the expected value of the payments under one leg must equal the expected value of the payments under the other leg, we can deduce from the above diagram that 6% times 60%, which is the total expected payment from the seller, must equal 94% times S plus 6% times S, which is the sum of the expected payments from the buyer. By saying that the seller pays 60%, i.e. 1 minus 40%, following a credit event, we are assuming specifically that the seller pays the face value of the bond that is delivered to him, but not any accrued coupon on that bond, and also that the 4% recovery value of the bond that he receives is inclusive of all claims for accrued interest under that bond. This is a little different from what we had assumed when solving for the coupon in our earlier discussion of the bond, but is necessary to eliminate the one extra variable that would otherwise be needed and that would give rise to an infinite number of solutions. Finally, solving the as above, we get 3.60% for S, the spread. You probably noted that the CDS spread of 360% is 32 basis points lower than the spread of 3.92% over the risk-free rate that we obtained under the bond. Remember, the coupon there came out to 8.92%. Is there an arbitrage? Does an investor who desires exposure to a reference entity always achieve a higher spread for the same level of risk by selling protection in the CDS market instead of purchasing a bond? Click pause to think about this question, focusing especially on two cash flow characteristics of the CDS that we have described that are different from a bond and that bring down the spread of the CDS relative to that of a bond. The answer is that this apparent arbitrage stems principally from one of the conventions we adopted in this example, namely that even when a credit event occurs, the protection seller will still receive, and the protection buyer must still pay, the accrued spread under the CDS up to the date of the credit event. Stated another way, when a bond defaults, the holder finds both his principal and his accrued interest in default and enters a bankruptcy proceeding with an unsatisfied claim for the sum of the two. Since here we are assuming that a credit event can occur only annually, it follows that the holder's claim in bankruptcy is certain to equal $1 plus the accrued coupon for 1 year, for which the recovery rate will apply to both. Under the CDS, however, the protection seller, replacing what was previously the bondholder, will suffer a loss on the notional amount of the contract based on the recovery value of the bond, but will receive 100% of the accrued spread from the protection buyer. So the quantum of risk assumed when purchasing a bond with face value 1 is marginally higher than the risk assumed when selling protection on a notional $1, therefore causing the CDS spread correctly to trade tighter than the bonds. Please note, however, that in our module on the cash CDS basis, we will discuss several other factors that also drive a gap between CDS spreads and bond spreads, sometimes in favor of one and other times in favor of the other. Note that we can generalize the formula for what we discussed above by writing for the spread S equals PD times 1 minus R, or 1 minus RV, which is just a way of saying that the spread equals the expected loss under the CDS. This looks very elegant for a 1-year CDS that has been simplified by the assumption that a credit event can occur only at maturity, but its fundamental insight should be consistent with your understanding of the pricing of financial instruments. Namely, that in a risk-neutral framework, there should be no free lunch, in the sense that any premium paid to any party for assuming any credit risk should equal the probability-adjusted loss expectation of that party, no more nor less. Reality is different, however, as we will illustrate in Chapter 2. By the same argument, if we already know the 1-year spread, we can write PD equals the spread over 1 minus R, so we can always extract the implied default probability for 1 year for any reference entity if we know its 1-year CDS spread, and subject to whatever recovery assumption we make. We are now in a position to examine how we might imply the annual default probabilities for 2 or more successive years if we have a more developed CDS curve for a reference entity. Assume the 1-year CDS for this reference entity has a spread of 360 basis points, and that the 2-year CDS has a spread of 400 basis points annually paid. We keep our original assumptions regarding the timing of a credit event, i.e. that it occurs only annually, the recovery value being 40%, and the risk-free rate being 5% for all maturities. From the 360 basis point 1-year spread, we know that we can derive a default probability for year 1 using our previous formula of 6%. Now we draw a diagram that shows the possible outcomes under the 2-year CDS, remembering that the spread is 4% annually under this contract. Here is the diagram, which is a little messier than before, but nothing too complicated, as you will soon see. In the present case, since the cash flows no longer all occur on the same date as they did in the example of the 1-year CDS, we need to set the present values of the mutual payments made by one party to the other equal to one another, which is the same thing as saying that the CDS at inception must have a net present value of 0. So we can write in present value terms 6%. We're now following the diagram up the first branch of the tree, times 60%, discounted using discount factor for 1 year. This is the first part of what the seller pays. Moving down the first tree's branch now, the lower branch, plus 94% times PD2, going up the second tree's first branch, times 60%, discounted using DF2, the 2-year discount factor. This is the PV of the probability adjusted total payments made by the seller. The buyer's total payments will involve more algebraic terms, but here they are. First, going up the first branch, 6% times 4% discounted. Going down the second branch of the first tree, plus 94% times 4%, again discounted for 1 year. Moving on to the second year's payments by the buyer in the last column, plus, and now remember, we are following the first branch of first tree's lower branch, and then the second tree's upper branch, so 94% times PD2 times 4% times DF2 to discount for 2 years, and finally, if we follow the two lower branches of the two trees, 94% times PS2 times the 4% payment times the discount factor. This right-hand side of the equation simplifies very visibly to this quantity here, and we remind you that DF1 and DF2 are nothing more than discount factors for cash flows occurring in exactly 1 and 2 years respectively. We know that discount factor 1 is equal to the amount shown here, 1 over 1.05, and DF2 is 1 over 105 squared, since the yield curve is flat at 5% for the risk-free rate. And solving for PD2 reveals a second-year marginal default probability of 7.41%. And finally, we solve for the value of PD2, obtaining 7.41% for PD2. It would be a good idea that you work your way through each and every step of this calculation until you are absolutely satisfied with its accuracy. It is very important to focus on the meaning of default probability and specifically the difference between conditional and absolute default probabilities. In the equation above, PD2 is the probability that the reference entity will default in year 2, assuming it has survived year 1. It is important to understand exactly what this means. If the reference entity has survived year 1, the probability that it will default at the end of year 2 is indicated by PD2. Whereas, if I stand at time t equals 0, i.e. up front, and I ask what is the probability that this reference entity will default specifically at the end of year 2, and therefore by implication not at the end of year 1, that probability would be smaller, since to default specifically in year 2, the company must first have survived year 1 with a probability of 94%, as we know, and then must default in year 2, where the probability of that happening is then PD2. This aggregate probability would therefore be 94% times PD2. We would call PD2 the conditional probability that the reference entity will default in year 2, and specifically conditional on having survived year 1, while the item 94% times PD2 is the absolute probability at inception time of the trade that the company will default in year 2 specifically. A somewhat macabre example from Russian roulette will clarify this point. If the process is about to begin with a gun that can hold 6 bullets, and I am second in line to put the gun to my head, the probability that I will be the unlucky one is, as of this moment, 1 over 6, or approximately 16.67%. But if the person ahead of me has already had his turn and has survived, then the probability I will be the unlucky one will have risen to 1/5 by that point, i.e. to 20%. To restate, the 20% is the conditional probability that the bullet will be in hole 2, assuming it has not turned up in hole 1. PD2 in our example is analogous to the 20% probability with the Russian roulette, while 0.94 times PD2 is analogous to the 16.67% probability in the example with the Russian roulette. You should have been able to recognize the similarity of this process to the one known as bootstrapping, in which zero coupon rates are extracted from a yield curve that provides the yields of bonds that pay periodic coupons, except for the first bond, which is assumed to be a discount security. Both methods rely on the idea that from the shortest available instrument in the curve, for which there is only one date on which cash flows occur, we can derive the unknown quantity, PD1 in our present case, from the remaining known quantities, in this case S1, the spread for 1 year, and RV, the recovery value, by solving an equation. And then we can move on to the next instrument down the curve and derive the next unknown quantity, which will be PD2 in our present case, from the remaining quantities, one of which was previously unknown, PD1, but has now become known, and therefore leaves only one unknown to solve for in the second equation. This process, of course, can now be repeated to derive from the 3-year CDS spread, PD3, and so on as far as the CDS curve reaches. Intuitively, the fact that in our earlier example PD2 came out to be so much larger than PD1 should not have surprised you. The 1-year CDS spread is 40 basis points, we remind you, lower than the 2-year, 360 versus 400, specifically, indicating a significantly higher probability of default in year 2 than in year 1. The equation we used to derive PD2 can now, of course, be written in a more general form. And we will just give the entire formula and trust that if you work your way through it carefully, following the exact methodology we taught before, you should be able to confirm the accuracy of this formula. Note we have switched here in the formula to saying CDS2 for the 2-year CDS spread, and to make the formula a little easier to follow, we use the notation PS1 for the survival probability for 1 year, and remind you that that is 1 minus PD1, and the same meaning for PS2. We could, of course, solve this equation for PD2, but the algebra would be very tedious, so we will rely instead on the goal-seek function in a special worksheet we have prepared called implied PD, to which we now turn. We begin first in the worksheet CDS implied PD by recalling that the 1-year CDS is 3.6%, and we'll assume initially that the CDS curve is flat. Therefore, the CDS for 2 years is also 3.6%. From the 1-year CDS, we know that we can derive PD1 in cell C4 to be 6%. We will go ahead and manually insert that. But of course, we could have just taken the 3.6% 1-year CDS and divided that by 1 minus RV. RV itself, of course, is not 50%, but rather 40%. The risk-free rate for 1 year is correctly inserted already as 5%. Now, for the time being, the worksheet assumes that PD2 in this cell C6 is 10%, plugs everything into the formula, and then, to simplify our programming, spits out 6 items that you see here that represent the first and second term on the left-hand side, followed by the first, second, third, and fourth terms on the right-hand side. This is done, as experienced Excel users know, to minimize the probability of a bad error in the programming. And finally, one very important cell, namely this one here, cell F10 contains the difference between the sum of the right-hand side and the sum of the left-hand side. And we know that a properly priced CDS at inception would require this difference to be 0, namely the NPV of the swap for 2 years. Right now this target number is not 0, presumably because our guess of 10% for PD2 evidently is not correct. So we resort to our old friend goal-seek and we set the cell equal to value 0 by changing that one remaining input which we are allowed to change in cell C6 and discover that PD1 and PD2 have exactly the same value. This is intuitive. If the market is charging no more for 1 year of protection than for 2 years, then the market is saying that both years are equally risky and therefore should have the same marginal PDs. We hope you have recognized here the parallel with interest rate forwards, where a flat curve implies that the forward interest rate equals the spot interest rate. We now go back to our earlier example in which the curve was not flat, but where CDS2 was actually 4%, and repeat the same process again. Once again, we have a target value in cell F10, which is not right now equal to 0. So we set goal seek, making this cell equal to 0 by changing the value of PD2 in cell C6, which we know has to rise since the flat curve gave us a PD2 equal to PD1, and therefore an upward sloping curve implying presumably more risk in year 2 than in year 1. Indeed it does, and it increases to 7.41%, the number we had seen before. In general, therefore, this confirms that a positively sloped CDS curve in a risk-neutral framework represents the market's view that year 2 is riskier than year 1. Please remember, the risk-neutral framework strips out any value for technical factors like liquidity and demand and supply and so on, and assumes that all CDS spreads are strictly definable by the variables PD and RV. We ask you now to predict approximately what the pattern for PD1 and PD2 will be if the CDS curve is inverted, with the 1-year CDS still at 3.6%, but the 2-year CDS, let us say, at 3.25%. Click pause until you are ready to hear the answer. We are ready to derive the value of PD2, and we do so once again by setting our target value in this cell F10 equal as usual to 0 by changing the existing value of PD2, visibly too high a value, and upon hitting OK we discover a value of 4.77% for PD2. Again, this is not surprising since the inverted curve suggests greater risk of default in year 1 than in year 2. And again, you hopefully have spotted the obvious parallel to the interest rate forward curve, which becomes inverted when the zero coupon curve is itself inverted. We conclude this chapter 1 by pointing out the limitations of the approach we have been describing for pricing CDS contracts and providing hints as to how they are addressed in reality. The first obvious limitation is our assumption that a credit event can occur only at the end of a year. You should be able to see, however, that we can address this by splitting the 1-year period into increasingly shorter sub-periods and proceeding with the same methodology, which will remain in essence the same, but will cause the algebra to become far more complicated. The parallel with the binomial tree pricing method for options should be obvious, and the ability to adopt continuous mathematics once the intervals become very short, which we do with options, applies just as much to the case of CDS. A more advanced quantitative module will illustrate this approach in detail for those in need of more precise pricing tools. A second limitation, as we discussed, is the model's need to fix recovery value at some number and to make no allowances for different recovery values for different types of credit events. For example, many CDS contracts include in the definition of credit event not only payment default and bankruptcy, but, as the first bullet point here mentions, also a restructuring of the reference entity's debts resulting from a distressed financial condition. And generally speaking, recoveries are substantially higher when debt is restructured than in an outright bankruptcy. It turns out, however, that we can address this limitation as well simply by increasing the number of branches at each node of the tree to separate a credit event based on bankruptcy or failure to pay from one based on a restructuring only, and then by using different values of RV for each of these scenarios. And lastly, as we have mentioned already, the model assumes that spreads are explained entirely from, i.e. they reflect exclusively PD and RV, default probability and recovery value, and that no other factors play a role in pricing. This is very far from reality, and therefore Chapter 2, to which we now turn, will examine the role of these other factors on credit pricing.